Hello students, this is the second video on magnetostatics, and in first video we have discussed the Biot-Savart law, and in this video I will discuss the divergence and curl of the magnetic field, and after that the Ampere's law and its applications to find the magnetic field for some special cases. As we know that the magnetic field can be created by the permanent magnet which have the north pole and south pole, and it have some magnetic field around it, and also the magnetic field can be created by some current carrying source or current carrying wire, and it was observed first by Oersted that the current carrying wire can create some kind of magnetic field around it, and the direction of this magnetic field can be found using the right hand law. And the right hand law is that if thumb is denoting the direction of current, then the curl of the fingers will show the direction of the magnetic field. Suppose the current is flowing in plus z direction here, then here the magnetic field will be, is coming out of the plane, and here this the magnetic field lines will go inside the plane. Now we will discuss the divergence of B, which gives us the Gauss law of magnetostatics, and the magnetic flux passing through a closed surface is given by phi equal to B dot dA surface integral. This is total flux, and the magnetic lines makes the closed loop. We have seen in last slide that the magnetic lines, they make the closed loop, and so the total number of lines entering equal to total number of lines leaving from the surface, and this will give us the total flux equal to 0. So that's why this flux B dot dA closed integral equal to 0, and using Gauss divergence theorem we can write the surface integral into volume integral, but this B will change to divergence of B or del dot B, and dA will be changed in dV. So equation 3, this equation is true for all volumes, so this del dot B should be 0. That's why this del dot B equal to 0 is known as the Gauss law of magnetism, and it states that the magnetic flux through any closed surface is always 0. Now we will discuss the Ampere's law, which is an important law for calculating the magnetic field, and it says that the line integral of resultant magnetic field along any closed path is equal to mu naught times the total current enclosed by the loop. So mathematically we can see that the line integral B dot dl along a closed path equal to mu naught into I enclosed, and if we see we have a current carrying wire and there is a Amperian loop, so I enclosed is I in this case, and if we have two current element, one is I1 and one is I2, in that case the total I enclosed inside this loop is I1 plus I2, and if one current is going in other direction, then we will write I1 minus I2. So the proof of this equation we can do it by using the magnetic field for a current carrying wire. So left hand side is the B dot dl, the line integral, and if we consider a wire and if we make an Amperian loop at a distance s, and we take a small element dl at point P, and B and dl are in same direction, so the angle is 0 between dl and B, and the magnetic field at point P, we already know that if we have a current carrying wire, then B equal to mu naught I by 2 pi s. So B dot dl will be mu naught I by I divided by 2 pi s into dl cos 0, that is 1. So mu naught, it will gives us mu naught I 2 pi s and the line integral of dl along this closed path, and this will give us 2 pi s, the diameter, the circumference of this 2 pi s, and 2 pi s will be cancelled out. So b dot dl equal to mu naught into I. So now this is the Ampere's law. This is the integral form of the Ampere's law. And if we know the current density, then we can also find out the current I using this relation I equal to integral surface integral j dot dA, because we know that j equal to I by A. And the Ampere's law in differential form gives us the curl. So we know, as in last slide we have seen, that Ampere's law in integral form was integral for a closed path, line integral for a closed path b dot dl equal to mu naught into I enclosed. And if we use the Stokes theorem, which can change the line integral into surface integral, so integral b dot dl equal to surface integral del cross b dA. So this del cross b dA equal to mu naught, and this I can be written as j dot dA. So del cross b dA equal to mu naught j into dA. And now we can compare the integrands, because both are same integral with surface integral. So if we remove the integral, then we should have del cross b equal to mu naught into j. So this is the differential form of the Ampere's law, and it gives us the curl of the magnetic field, which is mu naught into j. And now we have to apply the Ampere's law to find the magnetic field. So it is an efficient method for calculation of magnetic field for currents with appropriate symmetry. So we will see where we can use this Ampere's law. And Ampere's law have the same role as the Gauss law have in electrostatics. We have seen that we have found the electric field using the Gauss law in electrostatics, and with Coulomb's law it was difficult, but using Gauss law it was very simple. Similarly, the magnetic field can be found out by Biot-Savart law, which is a long method, but using the Ampere's law we can find out the magnetic field easily, or with simple method. And this is the integral form, integral b dot dl equal to mu naught I enclosed. This is the integral form of the Ampere's law, and the differential form is del cross b equal to mu naught into j. And sometimes I enclosed is the surface integral j dot dA. So this is the current enclosed by the Amperian loop. And now the application of the Ampere's law is, we can utilize this to find the magnetic field for some of the symmetries, because we cannot use Ampere's law always. And the configuration that can be handled by the Ampere's law are, we can use it for the infinite state current carrying wire, thin wire, and also thick wire or thick conductor cylindrical wire, for the infinite planes, infinite solenoids and toroids. So we will discuss some of these cases to find the magnetic field. First case is, find the magnetic field at a distance s from a long straight wire carrying a current I. So we have done this problem with the Biot-Savart law in last lecture. Here we will see using the Ampere's law. And if we have a wire which is carrying a current capital I, and we have to find the magnetic field at a point P, which is at distance small s from this wire. So first we will have to draw a loop, Amperian loop at point P, which is here a circle, and this at this Amperian loop we will use the Ampere's law. The Ampere's law is the line integral b dot dl for the closed path equal to mu naught into I enclosed in this loop. So left hand side is b dot dl equal to b, we can take outside because it is magnitude. The integral, closed integral of dl will give us dl, it will give us the 2 pi s. So b magnitude 2 pi s equal to mu naught, right hand side is mu naught into I enclosed. I enclosed in this loop is capital I, current through this wire. So we will have the magnitude mu naught I by 2 pi s, and the direction will be uh, with the this in if we want to get at this point, so direction will be in phi cap direction, 2 mu naught I by 2 pi s in phi into in phi cap direction. So Ampere's law is easier method to find the magnetic field, as we have seen that with the Biot-Savart law we have to do a lot of trigonometry and geometry to find out this relation. Now another example is, if we have a current carrying thick wire or a cylindrical wire is there, and the total current is at the surface of this wire. So we have, you can think at a cylinder which have a radius small a, radius is small a, and we have to find the magnetic field at inner point of this cylinder or inner point of this wire and outer point of this wire. So first, if we want to get the magnetic field at inner point P, so first we'll have to make an Amperian loop here at point P at distance s from its center. So at s distance we will use this Amperian loop, and now use the Ampere's law, B dot dl equal to mu naught into I enclosed. So in this case the current is on the surface of the current carrying wire. So inside this there is no current, inside, so I enclosed is 0, that's why this whole term will be 0, B dot dl equal to 0, that's why B equal to 0 inside at inside point, means when s is less than a, inner point. And for s is greater than a means when the point P is outside. Here we have to find the magnetic field at a distance s from this center of this wire. So in that case we will have to make the Amperian loop at point P at distance s. So again use the Ampere's law, line integral B dot dl equal to mu naught into I enclosed, and here we can take out this magnitude of B, and close integral dl equal to mu naught surface integral j dot dA. Mu naught can be taken out, and I enclosed is equal to j into dA, and j is because the current density is current divided by area, so j equal to I by pi a square, and I by j into dA. In this for z cap direction it is s ds d phi. So j dot dA can be written as like this, and the limits for this s, now because the for the outside point the current will be for the whole wire 0 to a, the limit will be 0 to a here, and for the phi total limit is 0 to 2 pi. And finally we have B magnitude B 2 pi s equal to mu naught I by pi a square. This pi a square can be taken out, s square by, because s ds means the integral is s square by 2 0 to a, and d phi has integral phi, and limit is 0 to 2 pi. So we have some many terms will be cancelled out. Finally we will have B vector or magnetic field vector equal to mu naught I by 2 pi s in phi cap direction. So this is when there was uniform distribution of current on this wire. But second case we will discuss when there is non-uniform. In this case also, this example is similar to the last example, only now we have the current distribution J equal to Ks into Z cap. So current is distributed in this cylindrical wire. So again we have to find out the magnetic field at the inner point and outer point. So if we take the inner point, we draw a Amperian loop at distance s and use the Ampere's law, close integral line integral P dot dl equal to mu naught I enclosed, and I enclosed is j dot dA, and j is given as Ks in z cap direction, and dA equal to s ds d phi in z cap direction. So it will give us mu naught k s square d phi ds. And if we integrate, because now the limit for s equal to 0 to s here, because inner point is there, and for phi 0 to 2 pi, and finally we will get s square will give us s cube by 3. So b will be mu naught k s square by 3 in phi cap direction. So this is for the inner point, and for the outer point, point P is here at s distance. Again, draw a Amperian loop at point P, and now in this case the total current will be the from 0 to A, because whole wire is inside this loop. So in this case only there will be change in the limit of s 0 to, instead of 0 to s we will take mu naught 0 to A, phi will 0 to 2 pi, it will be ks s ds d phi, and finally we have instead of s cube by 3 we will have a cube by 3, and finally we have the answer mu naught k a cube by 3 1 by s in phi cap direction. Now we will see an example for the magnetic field due to a current in uniform sheet. So if we have a sheet in xy plane and the current is flowing in x direction, plus x direction, and the surface current is denoted by k into x cap direction, and if we take an Amperian loop like this, rectangular loop here, and now we have to find out the magnetic field the above of in plus z direction and minus z direction, here and here at 2 points. How we will find the magnetic field? So again we will have to use the Ampere's law at Amperian loop. Now we have the current loop like this, 1 2 3 and 4 line segments are there, and current is flowing in x direction, and the direction of magnetic field is in y direction. And we can see that if k is the current density, and now we have to use the Ampere's law to this Amperian loop. So it will be closed line integral of b dot dl equal to mu naught into I enclosed, and this now b dot dl closed loop equal to can be written as line segment 1 2 3 4. We can add these all line integrals, and we will see that 2 and 4 will vanish, because the line element dl is in this direction, magnetic field is in this direction, so angle theta equal to 90 degree, so that b dl cos 90, that will give us 0. So 2 and 4 will give us 0, so only contribution will be from the segment 1 and segment 3, and segment 1 and 3 will give us bl plus pl, that is 2bl equal to mu naught into I enclosed, and I enclosed is equal to surface current density k into L. L was the length of this loop, so it is mu naught into k into L. L and L will be cancelled out, so B will be mu naught by 2 k. And the direction, if we it is plus z above and minus z below the that sheet, and if z is less than 0, so current is flowing in x direction, so fingers will curl around plus y direction. So for z is less than 0, it is mu naught k by 2 in y cap plus y cap direction, and if it is above z, then the current is flowing in this direction, so here the direction will be in minus y direction, minus mu naught by 2 k into y cap for z is greater than 0. So we can see from this expression that field is independent of the distance from the plane, and it is just like the electric field due to the sheet of charge or surface charge sigma we have seen in electrostatics, that electric field was sigma by 2 epsilon naught, that also does not depend on the distance. Now we have to find the magnetic field for a long solenoid which have n number of turns per unit length on a cylinder of radius r, and which is carrying a current capital I. So this is, we have a long solenoid and the wire have n turns and capital I is the current in this wire. So we have to find out the magnetic field at outside point and at the inside point of this solenoid. So first we take the case of point P is outside. So in that case if we take Amperian loop at point P, and we will see that inside this loop there is no current enclosed. There is no current enclosed. So right hand side, Ampere's law is close integral of B dot dl line integral equal to mu naught into I enclosed, and I enclosed is 0, so that's why B equal to 0. So outside the solenoid it does not depend on the distance, and at large distance it goes to 0. So outside point it is 0, and for the inside point we take, at suppose this is the point P, so we will make a Amperian loop here, and this Amperian loop we have the segment 1, 2, 3 and 4. So again we use the line integral B dot dl equal to B dot dl for 1, 2, 3 and 4. These 4 segments are there, and we will see that the contribution is only for from the this point this segment 4, because 1, in case of 1 and 3 the angle is 90 degree with the magnetic field, so 1 and 3 will give us 0. 2 is B dot dl for the 2 equal to B equal to 0, B equal to 0 because it is outside. This line is outside, line segment is outside of the solenoid, and outside of solenoid is B equal to 0. So that's why only contribution is from the fourth segment. So it will B dot L give B L cos theta. So B L equal to mu naught into I enclosed, and I enclosed is this N into I into L, because there are n number of turns are there. I is the current and L is the length of this Amperian loop. So we will have B equal to mu naught N into I. This is the magnitude, and the direction will be in z cap direction. So B equal to mu naught N I into z cap inside the solenoid, and for the outside it is 0. Now we have to find out the magnetic field of toroid using the Ampere's law. And toroid is a hollow circular ring which have a large number of turns of a wire, and those are closely wound on this kind of ring. The wires are wrapped around this, and in a toroid all the magnetic flux is contained in the core material. So inside this and outside this is no magnetic field. So inside point S is less than a B equal to 0, and also at outside point B equal to 0, because here is no current, and for outer point the currents flowing in this inner and outer loop, they will cancel out. And now we have to find in the core or axis of this toroid S point, when S point is between A and B. So inner radius is A and outer radius is B. So we have to take the magnetic field at some point which is at S distance. So make the Amperian loop. Here we have this blue dotted circle. So now we have to apply the Ampere's law, integral B dot dl equal to mu naught into I enclosed. So B magnitude into 2 pi s. So integral dl will be 2 pi s equal to mu naught into I enclosed. And again the I enclosed for this, if we have the n number of turns, and it will be mu naught I n into I divided by 2 pi s. So this is the magnetic field at inner point or inside the coil, and it is 0 the point outside of this toroid. So n is the total number of turns. So this is how we can find out the magnetic field at the axis of the toroid. And toroid is used in inductors, in the electronic circuits, and also it is used for the tape heads to big devices like tokamaks. Tokamaks are the device which use the very high magnetic fields to confine the plasma in the shape of torus or donut. In this kind of shape, high magnetic fields are used. So this is how we can find out the magnetic field for the toroid. So in this video we have discussed the Ampere's law, and in previous video we have discussed the Biot-Savart law, and in next video we will discuss the electromagnetic induction and Faraday's law. So thanks for watching this video, and if you are new to this channel, then please subscribe so that you can have the information about the new videos on the topics of electrodynamics. Thank you very much.